Hi, welcome back to Mr. Slover's Math. Today we're going to focus on key features of linear functions. So let's backtrack. Linear functions, remember, is just a straight line. Key features is a way to describe in detail that line. So let's think of a non-math example. If I talk about someone named Andrew, right now all you know is his name. But if I give you some features of him, that he's maybe 5'7", he's got short hair, he wears glasses. Now you have a better understanding of what Andrew looks like. It's the same idea for what we're doing today. So our key features, we're giving more detail to what our line or our function looks like. So in order to do that, there's a few phrases that we need to know in terminology. So the first one is our intercepts. We've talked about intercepts before when we were graphing, especially the y-intercepts, but we really haven't talked about the x-intercept. So our x-intercept is where the graph crosses the x-axis. Think about that. Hopefully it makes sense. X-intercept, x-axis. The y-intercept we've used before when we were graphing linear functions. Your y-intercept is where the graph crosses the y-axis. So our example says, find the following for the graph to the right. So I am looking for these as an ordered pair. Sometimes teachers accept it just as your x-intercept is 4 or your y-intercept is 3, but I'm looking for ordered pairs. I want to know where on the graph is the x-intercept. Because if I just tell you 4, that's not really a location on a graph. That's just a number. But if I tell you 4, 0, I know where that is on the graph. Everyone knows where that is on the graph, provided they know how to label a point on a graph. Right? And then our y-intercept on this one is at 0, 3. Now notice over here in red, I gave some helpful information. Your x-intercept always has 0 for your y value. And your y-intercept always has 0 for your x value. So think about it. The 0 is in place of what you're not trying to find. So x-intercept, my y value is 0. Y-intercept, my x value is 0. The next term that we need to know is our domain. And the domain is the x values in a set of ordered pairs, or what the x values could be on a graphed line. So we're going to start with the basic of ordered pairs. So we have an understanding of what the domain is. So the first one is I'm going to look at this set of ordered pairs, and I'm just going to list my domain. I'm going to list my x values. So 1, 2, 3, and 4. And then over here, I'm going to use this graph. Now, in red, I had to write out where these ordered pairs were, where these points were located. So I had to write these ordered pairs. I'm going to use the x value to figure out my domain. So B has a domain of -4. Point A has a domain of 2, and 0, and 7, and -3. So that's how I came up with my domains. Now your domain is your x value, so that means we need something for our y value, and that's what the range is. The range are the y values in a set of ordered pairs, or what the y values could be on a graphed line. So once again, I'm using the same information that I just used up here, the same set of ordered pairs on the same graph. But now I'm focusing on the y values. So 5, 6, 7, and 8. And then same thing over here. I'm using the same graph. So I already listed all my ordered pairs, so I'm not going to do more work than I need to. I'm just going to look up here and identify my y values. And they can be in any order. Right, so up here I had numerical order, but here I don't, just to show that it doesn't matter what your order is. Okay, so now we get into a little bit more complex things. And so we talk about end behaviors. And this says, as x approaches -infinity, f of x is what? Okay, and I kind of wrote out what this top line is saying here and what this bottom line is saying here. So first off, let's figure out what this means. I have a positive and negative infinity. Well, infinity is obviously very large by definition. So we need a way to kind of pinpoint what direction we're looking at. So we're going to say negative infinity. If I tell you negative infinity, you know that it's all numbers to the left of 0. If I tell you positive infinity, it's all numbers to the right of 0. So you have a direction. Whereas if I just said infinity, you would have no idea whether it's positive or negative. Okay? I'm trying to give you a little bit of direction on where we're going. So right now our end behavior, it says as x approaches negative infinity, so these are my x values. What are my y values going to be? Okay? F of x, remember, is a fancy way for us mathematicians to sometimes say y values. What's my y value? Well, my y value is going to be positive infinity. Okay? It goes up towards positive infinity. Or it could go down to positive, or go down to negative infinity. Okay? This is just an example. Okay? This is going to make more sense when we actually do an example, but I need to introduce what the end behavior is. So this one is the same thing. This is saying as x approaches positive infinity, so as my x values approach positive infinity, what do my y values look like? And that's what it's asking. So let's see this in action. So example 1 says list and label the key features of the linear function, meaning I need to look at this line and I need to give some more detail. So here's my line. My slope-intercept form, my x-intercept, my y-intercept, my slope, domain, range, and end behaviors. Those are the key features that I'm looking for, and those are probably the key features you're going to see on and off throughout the semester if you're identifying key features of functions. These can be you don't have to solve these in any specific order. You can answer these any way you want. Okay? Sometimes it's easier to answer certain ones first over other ones, but for the most part, the choice is yours. I'm just going to go kind of in order. I am going to skip the slope-intercept for now, and you'll see why in a minute. So first I'm going to look at the x-intercept. So I remember the x-intercept is where it crosses the x-axis, and I want that as an ordered pair. So here's my line, crosses the x-axis. It says x-axis, right? X means x-axis. At -2. I went left 2, and then I did not go up or down. So my x-intercept is at -2, 0. My y-intercept, so here's my y-axis. I went down 3, so I didn't go right or left. I went down 3, so that's why it's at 0, -3. My slope. I'm choosing to use my 2 intercepts. You can use any whole points that you want on here. Okay? And I've talked about whole points before, but to refresh your memory, your whole point is I want where my line goes through like the corner of this box. Right? If I'm right here, kind of where my cursor is, that's not really a whole number. I don't know where that is, right? But I know for sure that that's at -2, 0. I'm 100% sure that that's where that is. Not so sure where this point is. So I pick these 2 points, and I count my rise over run. I'm figuring out my slope. And it doesn't matter whether you start with this one or this one. You get the same answer. So I'm going to start with this one. I went down 3, so because I'm going down, that makes it -1, 2, 3, and I went right 2. My slope is -3/2. Well, now that I know my slope, I can go ahead and it makes it easier to figure out the slope-intercept form. Your slope-intercept form is y equals mx plus b. Well, I just found the slope. I know what the y-intercept is. I just have to write my equation. So y equals -3/2 x minus 3. That's my slope-intercept form. Now, my domain and range. My domain is my x values. So my x values is right here, my x-axis. What this means is if my x value is way over here at -6, does my graph exist? Does this line exist somewhere at x equals -6? And yeah, I can draw a line straight up and it's going to intersect that line. Well, your graph does not stop at -6. It actually keeps going infinitely to the left, which is why we talk about negative infinity. So as this goes further to the left, to negative infinity, will it intersect my line? Is there an x value that could be on this line? And the answer is yes, because this line extends infinitely up and to the left. Likewise, my x-axis extends infinitely to the left. So there is going to be some sort of x value anywhere in the negative infinity range. And I do the same thing for my going the other way. So x is positive infinity. Will my graph exist? And the answer is yes. I can have a number way over here on my x-axis, and I'll have an x value that intersects my line way down here. That's okay. So my range is very similar. I want a y value. What could my y values be? Well, my y values could be, if I start at negative infinity, so way down here, my graph does exist way down here. I would have a y value that could go on that graph. Same thing with the positive infinity. So purposes of this class, I am always going to give you a function that has a domain and a range that's negative infinity to positive infinity. I could have any x value or any y value, and it would create a point on this graph. That's what your domain and range are talking about. Any x value or y value will create or could create a point on this line. Now, if you are in a different math class than the one I'm teaching, that may not necessarily be the case. Your domain could change or your range could change. It just depends on the information that you were given by your teacher. But for purposes of my class, your domain and range will always be the exact same. Your end behavior. So this is saying as x approaches negative infinity, what's my y value? Okay, so that's what it's saying mathematically. We're going to think about this in a slightly different way. As x approaches negative infinity. Well, let's just look at my graph. Negative infinity is over here on the left side. Where's this pointing? Is my line pointing up to positive numbers, or is it pointing down to negative numbers? Well, it's pointing up to positive numbers. So my end behavior is positive infinity, because this graph keeps going up positive infinity y values, way up top. And then I look down here. The second one, as x approaches positive infinity. So now my x values are way over here, where my cursor is. Where's my line? Well, I just look at my line. Where's this pointing? Well, it's pointing down. Well, if it's pointing down, that means I have negative numbers, or I have negative infinity. So the easiest way to think about these end behaviors is to just look at the graph. Where's this pointing? Pointing up to positive numbers, positive infinity. Where's this pointing? Down to negative numbers, so negative infinity. Okay, that one was graphed for you, and the rest are not graphed for you. So you're going to have to graph the other ones. Okay, the only thing I want to point out in example 2 is that this y equals x is called your parent function. I'm not going to get into a whole lot of detail about the parent function right now, but that's just the basis for all of your transformations when you get there, if you get there. Right? But I want to look at a different example. So I want to look at example 3. It says graph and then list the key features of the linear function. So I give you the function. So right there, I already have one answer, slope-intercept form, y equals negative x plus 4. And I'm asking you to graph it. So in order to graph it, I need to know what the slope is. Well, it says negative x. Well, that means my slope is negative 1 over 1. I encourage you to always write your slope as a fraction because you're going to have to graph it. My y-intercept is at 4. I got that straight from the equation. So I started at 4 on the y-axis. I went down 1, right 1. So that's why I wrote it as a fraction, so I know I was doing two things, going down 1 and right 1. Down 1, right 1. And I create my line. Once I have that graphed, I can find my x-intercept where it crosses the x-axis, where it crosses the y-axis. Your domain and range, remember, for purposes of this class, could be anything. My x could be any value, and I could have my graph would exist. Same thing with the range. I could have any y value, and my graph could exist. My end behavior. So all I have to do is negative infinity. So I'm over here. Where's this pointing? Well, it's pointing up. Well, up is positive, so positive infinity. Where's this one pointing? Negative infinity, because it's pointing down. Example 4, you just had to get it in slope-intercept form, and then everything else is still the same. Notice your domain and your range are not changing from problem to problem. They are still negative infinity to positive infinity, because your x and y could be anything, and you could have your graph existing at any x or y value. And then at the bottom is just some true or false. So this information, this key features, is just us looking at a line, giving more detailed information about that line. Okay? At times, yes, it can be a little confusing, but just break it into manageable pieces. You can go in any order to answer these key feature questions. You don't have to focus just on the slope-intercept form. You can skip it and go back to it, or go in any order. So if you have questions, make sure you reach out.